Uh, the continuation of our class yesterday, uh, it was basically the fundamental or the introduction to electrode dynamometers. Like we have earlier pointed out during our previous discussions, uh, dynamometers can be used to measure both AC and DC. Yesterday, we are able to establish the relationship between the deflection angle for DC. Now today we continue, and today we are going to take the AC part of it. And AC is nothing but that which varies with time. Unlike DC, we know that DC, if this is the graph, DC graph, what this implies is if this is our time and this is our voltage, for instance, let's say 2 volt at this point. For DC, this 2 volt remain constant. It never changes with time. You can see it's straight. If it is 0.5 volt, let's say this is 0.5 volt. It means from this point here, it's continued to remain 0.5 volt. Which means if this is 0 hour, at 0 hour it will be 0.5 volt. At later 2 hours it remains that. At later 3 hours, so that is DC. But AC is not like that. AC varies with time. As time progresses, the wave changes with time. And the usual form is the sinusoidal form, which is this. Is that okay? Now, we should recall that our torque, deflecting torque, is equals to I1, I2 multiplied by dm divided by dt. You know what I1 and I2 is from our earlier diagram. Now for AC, current changes with time, just like I have explained, and therefore the instantaneous torque, which means that the torque, which is defined as this one, because this one varies with time, it means that this will be instantaneous. That means at every point in time, how does the voltage changes? Is that okay? Now which implies that that is now instantaneous, not the deflecting torque directly. So the instantaneous torque, because you know in the earlier class we have made mention of the pointer changes as the voltage changes with time. Maybe it moves from 0 to the peak, it goes down, and you said in most times it's just to be vibrating at a point. That's what we said. Now instantaneous means that I1 dot I2 dm d theta. That is the instantaneous torque. Now assuming that the coils are connected in series. If the coils are connected in series, it is very, very obvious that the current that will flow through the coils will be equal. So that makes the coil through the I1 and I2. You can refer to that diagram in our last class, our yesterday class. I1 equals to I2. And if we say to select that to be equals to I, then that makes our instantaneous torque to be equals to I square dm d theta. Now that means that I is directly proportional to I square. As I varies, so does the instantaneous torque varies, which is very natural. We know all of this from the beginning. But due to inertia of the moving system, we have discussed that it cannot follow such a rapid variation of Ti. That's what we said. Because this changes with time, this will not be able to respond instantaneously, especially at high magnitude. It will not be able to respond. So what is done is the average TD is computed, which is around here. The average is computed around there, which is average, which is V average, right? That is what will be computed, and that's T average that is going to be TD, which is equals to, and like we are saying, is an average. Just like if you're having if you're having 1, 2, 5, 9, and you want to find the average of this, you take the sum of this one and divide by the total number 1, 2, 3. Now we are looking at a complete cycle from this to 2 pi, 360 degrees, or 2 pi radian. It means the average is going to be summation of all of this one, which is going to be in an integral form, and that is why you have this one from 0 to theta. Do you understand? Of t high variation, because this changes. It gets at this, it changes with time, you get to peak, it goes down, goes to 0, it goes down, and it goes like that. So t high dt, that means summation of this one from this, then the average, it means from here to this one, just like we have all of this total number. So that makes 1 divided by t, which is the total cycle. And from there, this one, you can substitute this one from this very equation. You substitute that into this one, and we have 1 divided by t. This is a constant because this is changes with time. The V or the AC changes with time from 0 to pi to 3 pi along this pi. This is our time. So that makes this to be independent variable, isn't it? And this one as a dependent variable, which means it's going to be dt, which is this one, isn't it? And therefore, since this one is dt and it is I now that is now varying with respect to the T now, because AC can be AC current, AC voltage, but like we said in the PMMC, it uses the current. Can say the current to measuring the V, the I, the resistance, depending on the way you configured it. So which means that this now is going to be 1 over T dn the theta integral 0 to this one, since this one is constant. Then at stable condition, we have said that before, TB is equals to TC. You see, the meters are such designed that the TD should be equals to TC, so that if the pointer is deflected or displaced, once that uh, uh, signal is removed from it, it should be able to go back to its reference point, to 0 point. Then, which means that TD is equals to TC, that is at stable condition. And that implies that TC is equals to KT equals to our TD here. So by the time you do all of this one, you end up having our T to be equals to the whole of this one. And this is exactly the deflection as a function of the means of the square of the current, which is this. So we discuss more on this when we meet physically in the class, and there are questions, then we also look at it on the platform. Thank you.